Okay, welcome to another lecture of data structures and algorithm. We have covered so far various topics, and the last topic which we covered was hashing. The contents are already uploaded on CMS and the lectures have been shared with you. Although the topic to be covered after hashing is B trees, but I am skipping it for a while. We will be covering it, right? We will be covering it, but I am skipping it for a while, and instead I am moving towards the topic of graphs and various lectures on graphs, because our semester project will be based upon this. So I thought it's better to cover graphs first, and then I'll be giving you the semester project, and while you are doing your semester project, I'll be covering the rest of the lectures on B trees, right? So this was a bit of a reason to change the sequence of lectures a bit, but we will complete the contents inshallah. So graph, like linked list, like arrays, like so many other things, graph is also a data structure which is used to store information of a particular type. For example, the graph has certain items known as nodes. For example, let me draw a graph here. For example, this is a node, this is a node, this is a node, and for example, this is a node, right? So these red points, these are called nodes. Nodes, and these are also called vertices, right? These are nodes or vertices, right? So in real world, these nodes may represent multiple things, right? For example, rather let me first complete this graph, then I'll be giving you an example. And then these nodes are connected with each other using edges, right? So we can call them edges, we can call them arcs. Now before drawing an edge, rather let me label these nodes as well. For example, let us give this node name A, right? And let us name this node as, oh sorry, okay, let us name this node as B, and this node as C, and this node as D, right? So we can have labeled nodes, and these labels can be alphabetical, they can be numerical, alphanumerical as well. For example, this one A can be 1, B can be 2 as well, right? So these nodes are connected with each other through an edge, right? So this green line is called the edge. Edge, or it's also called the arc. Oh. Right. So similarly, this node A can also be connected with B, right? So the whole of this is called a graph, right? And these edges can, if you see here, the edge from A to B do not have any direction. So this is undirected edge. It means through this edge you can go from A to B, and from B to A you can come back as well. But for example, if I put a direction on it, now this is a directed edge, right? It means that using this edge we can go from A to B, but we cannot come back from B to A, right? So once I have put the directions on this graph is now a directed graph, right? But if there were no directions on the edges, then this would have been a graph, and we would have called it an undirected graph, right? Now theoretically this graph is denoted as G, which comprises of two sets, set of vertices, these are the vertices, and set of edges, these are the edges, right? So these vertices, this set is represented as 1, 2, 3, 4 and 5 up to 6. So if you see here this example has 6 vertices, whereas the edges, if you see this edge do not have any name. So if we want to give it a name, since this edge is between 1 and 2, so we call it a 1 comma 2, right. So this edge is represented like this. For example, if this node was like A and this node was like labeled as B, so we would have written it as A comma B, right. So and as I told you earlier, this graph, if you see this graph, the edges do not have any directions, so this is an undirected graph. Right, now if we see here, it's the same graph which was in the previous slide, but here we have directions on the edges, right. So now this one is a directed graph, and this direction restricts our movement across the graph, right. And earlier I was mentioning about an example. For example, if we see this graph, these nodes may represent some real world entities. For example, these nodes may represent cities. This may be city number 1, this may be city number 2, city 3, 4 and 5, and these edges may represent the road network between these cities. So it means that there is a direct node from city number 1 to city number 2, but there is no direct road between city number 1 and 3, right. But maybe you can go from city 1 to 2, then 2 to let's say 5, and 5 to 6, and from 5 to and from 6 to 3, and this way you can reach city number 3, right. So these graphs basically represent an entity in the real world depending upon the problem statement at hand, right. And on these edges there is supposed to be a weight as well. Now by default, if an edge is present between two nodes, so the weight on the edge is 1. Now if you see here, there is no edge between 1 and 6, it means the weight here is 0, right. Now there are certain concepts in the graph. For example, the concept of a path. So path in a graph is sequence of vertices W1, W2 up to Wn, such that these Wi and Wi plus 1 is a subset from an edge. Now to demonstrate it visually, if you see, for example, this is a node or vertex, both are the same. This is another node, this is another node, and this is another node, right. Now from A I go to I connect B, and I connect C and D, and let me connect A and D as well. Now here to show you a path, this from A to B and B to D, and then from D to C, this is a path. Now these lines are basically the subsets of the set of edges, right. So this is called a path, and the length of the path is equal to the number of edges in the path. Now if you see there, how many edges are there? Oh sorry, I just rubbed it. Okay, let me draw it again. This is a graph. I've changed the colors, and it's like this. Okay, this is the graph and the path. Let me show the path using blue line. So I make a path from this point to this point, and let's say to this point. So there are 3 edges, so the length of this path is 3, and there are many other paths as well in the graph, right. A loop in the graph is an edge from a vertex onto itself, right. So let me try to make a loop using pink color, rather let me make it using red color. So from this vertex onto itself. Now this is a loop, right? From the same vertex you come back to itself, right? So this is a vertex. So the path concept is clear, length is clear, loop concept is clear, and simple path. Yes, this simple path concept is important. For example, consider this same graph, okay, and let me draw, no, rather this blue path, for example, from node A, this is B, this is C, and this is D. Now these blue lines show us a path. So from A we go to B, from B we go to C, and from C we go to D. Now this is a simple path. A simple path is a path where no vertices are repeated, right? So let me demonstrate to you a path which is not a simple path, right? Let me use this pink color, right? So let me draw a path. For example, from A we come to B, from B we come to C, from C we come to A, and from A we come to B again, and from B we come to again C, right? So here these A, B, C, these paths are repeated. So this pink path is a path, fine, but it's not a simple path because the vertices are getting repeated on its way, right? Okay, that's done as well. And then the final, there are other definitions as well, but the final definition for this slide is the cycle in the graph, right? So a cycle in the graph is a path which starts from a node X, and after moving to other nodes it comes back to that particular node itself. Okay, let me draw it for you. For example, this is a graph, and let us draw edges, right? From here we have these edges, right? And let me make a path. Now we start from this node, we come here, and then from this node we come here, and then from this node we come here, we come back here. Now this is a cycle, right? So in the cycle, the node from which you started, you go to other nodes and you come back to the same node. So this is called a cycle. And then there are certain other definitions in the graph which involves the concept of connectivity, right? Now a graph is said to be connected if there is a path from every vertex to every other vertex, right? Okay, let me draw it here. For example, this is a vertex. I'm using the terms vertex and nodes interchangeably because both are the same. So this is a graph which I have made, and let me connect these graphs. Like, let me connect it. Now here, okay, I have to label them as well. For example, let us label it as A, B, C, D, and E. Now this graph is connected. Okay, this D is okay, D. Now this graph, a graph is said to be connected such that from every vertex you can go to every other vertex, right? Now let us see if we can go or not, right? Now if you see here, from A I can go to B, right? There is an edge, but apparently from A I cannot go to C. But no, we can. For example, from A we go to B, and from B we go to C. So this means that A is connected with C through node B. Similarly, from A I can go to D as well directly. From A I can go to E as well, not directly, but from A I can go to D, and then from D I can go to E. So this graph satisfies the definition of a connected graph. Oh, sorry. right. So this is a connected graph. Now maybe I can draw another graph as an example of an unconnected graph. For example, this is node, this is node, and this is node, and I draw edges between them. That's all. Right? So this graph, this is not a connected graph because from this node you can go here, from here you can go back here, but you cannot reach this particular node. So this graph is not connected. Right. Okay. Then there is a within the category of connected graph, there is a concept of strongly connected graph, right. Okay. Now what is a strongly connected graph? A graph which is a directed graph plus it is a connected graph, it is called a strongly connected graph. Let me make it for you. For example, these three nodes, and then we have edges between them which will be directed edges from, right. Now here, okay, this arrow got sort of, right. Now if you see here from, okay, let me label them as well, A, B, C. Now edges have direction. From A I can go to B, from A I cannot go directly to C, but from A I can go to B and then C, then it's fine. And similarly from B I can go to C, and from B using this edge I cannot go to A, but okay, no problem. From B I go to C, and then from C I go to A. So it means every node is connected with every other node, plus the edges in the graph are directed as well. So this particular graph is a connected graph since the edges are directed, so that is why it is called strongly connected graph, right. And then there is another category within the connected graph which is called the weakly connected graph, right. Oh, okay. Now, what is a weakly connected graph? Let me draw it for you, and then you will be able to perceive it. Okay. Let us draw edges as well. Now, if you see here, from this node we go here. Okay, let me connect this as well. From this we can go here, and the direction on this edge, let me make it like this, and let me make it like this. Now let us label this node as A, this will be B, this will be C, and this will be T. Now if you see, from A we can go to B, from A we can go to C through this node B, but from A we can not go to D. For example, if we go from A to B, fine, we can go. From B to C we can do that, but from C to D the edge is directed on the different direction. So it means that this graph is not connected. But if we assume that these directions, if we ignore the directions, then if we ignore the direction, then this graph is a connected graph. So such graph is called a weakly connected graph. Theoretically, a graph, when it is directed, it is not connected, but if we see the underlying undirected graph and the underlying undirected graph is connected, so such graph is called a weakly connected graph, right. So these were a few definitions of various types of the graph: connected graph, strongly connected graph, and the weakly connected graph. This I've told you with examples. Now there are a whole range of applications of graphs in various domains, and for example, these graphs can be used to make driving maps. For example, you can represent cities using nodes, and you can represent the road networks between these cities using edges, right? Similarly, air traffic control air traffic control system uses graph-based representation, representing various routes of the aeroplanes using graphs. Similarly, the computer networks, they can be represented as graphs as well, and the VLSI design, which is basically a sort of a breadboard type stuff fabricated with ICs over it. So these can be represented as graphs, and then the goal of representing these problems as graph is to perform various operations on these graphs. For example, when you have a driving map, so the goal will be to find path from one node to another. Ultimately, you will be finding a path from one city to another, or within a city you will be commuting from source to the destination, right? Then from the data structures point of view, there is an important concept because we will be dealing with storing these graphs into main memory. So there we have got two options for storing these graphs into in the main memory or in the hard disk. The one is called the adjacency matrix, and the other one is called the adjacency list, right? So let us draw a graph, and let me explain to you the adjacency matrix first, right? For example, this is node, this is a node, and this is a node. And let us label this node as A, let us label this node as, okay, oh, I have to redraw, sorry. Let us label this node as A, and let us label this node as B, right? And let us label this node as C, right? And let us draw edges between these nodes. Okay, I am connecting only these two nodes A and B, right? Now, the adjacency matrix representation of this graph will be a two. If you see here, how many nodes are there? 1, 2, and 3. So we will be making a matrix with 3 columns and 3 rows, right? So first column, second column, and third column, right? This is first row, then second row, and third row, right? This first column will represent A, the second column will represent B, the third column will represent C. Similarly, this will be A, this will be B, and this will be C. Now, come to the graph. Now, if you see here, A is connected with B, we will go to this row, and we will put 1 between A and B, right? Now, B is connected with A, we will come to this row, and we will put 1 between B and A, right? And there are no other edges, right? So, for example, if we had another edge, for example, from B to C, right? So we would have put a 1 between B and C. Similarly, C is not connected with A, so we are not going to put anything here, but C is connected with B, so we are going to put 1 here. Now, the rest of the entries in this adjacency matrix, which is basically a 2D array, will be converted to 0, right? So this is the adjacency matrix. This is how we store a graph in a 2D array, which is known as the adjacency matrix. Now, for example, if you lose track of this graph, but you have this matrix, you can create this graph maybe in a different orientation. For example, let's assume that we do not have this graph and we have to reconstruct the graph using this adjacency matrix. So we know that this is a 3 by 3 matrix, so we will be having 3 nodes. The first node will be labeled as A, the second node will be labeled as B, and the third node will be labeled as C. Now we know that if we say A is connected with B, we will draw an edge between A and B. B is connected with A, since it's an undirected graph, so that is why this edge represents both ways, this one and this one, right? And then we go to this, we come to this row of C, and we see that C is connected with B, so we will be drawing an edge between C and B, right? We could have drawn this edge using this information as well. So the same graph, this graph and this graph both are the same, only the layout or orientation of this graph is different, right? So since I've labeled these columns and rows and A's and B, but in real life these A's and B's are not available as an indices, so practically this will be 1, this will be 2, and this will be 3. You can always map between 1, 2, 3 and A, B and C, right? So this is the adjacency matrix representation of the graph in the main memory. Now talking about the space complexity, the amount of space it will require. Now for example, if a graph, if we see here, this graph has 3 nodes, so the adjacency matrix is a 3 cross 3 matrix, right? But if we had n nodes, then this would have been n cross n. So the space complexity of the adjacency matrix is order of n cross n. This is the space complexity of adjacency matrix. The other representation or the other data structure to store the graph is called the adjacency list, right? Now the adjacency list is a bit different, but I will be representing the same graphs using adjacency list. In an adjacency list, we have 1D array which has cells equal to the number of nodes. For example, here we have 3 nodes, so we will be having 3 cells. The first cell will store A, the second cell will store B, and the third cell will store C. Now if we see A is connected with B, here we will be drawing a linked list. We will create a node and this will contain B. Now if you see here, B is connected with A, so we will make a node and we will place A here, and B is also connected with C, so we will make another node, we will draw C here, and C is connected with only B, so we will make a node and we will store B here, right. So this is the adjacency list representation of the same graph, right. And if we talk about the space complexity of this this data structure, which is the adjacency list. Now if you see here, the number of cells is equal to the number of nodes, and these number of nodes is equivalent to the number of edges, although they are repeated. So the space complexity of the adjacency list is order of V plus E, right. So this is the space complexity of adjacency list, right. So so the adjacency matrix is a 2 by 2 matrix, which I have already explained. The diagonal on the adjacency matrix is always contains 0 because when there are no loops in the graph, right. Otherwise, if there is an edge between node I and j, one value of 1 is placed there, right. And the space complexity, as I told you earlier, of the adjacency matrix is order of n square, right. And the adjacency list I already explained to you, and its space complexity is order of v plus e. But adjacency matrix has its own advantages and disadvantages. For example, let me make a graph here, and for example, this is a graph with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. For example, so many edges. Let's assume that these are 100 nodes. Sorry, I said edges. These are nodes, right? So and only 2 of these among these nodes are connected. So for this, we will be making a matrix of 100 cross 100, where only 2 cells, cell between I and j and the cell between j and I, only 2 cells out of 100 cross 100s will be consumed. So adjacency matrix is very sparse it's sparse when the graph is rarely connected, right. There is a term for a rarely connected graph which is called a sparse graph, right. For example, this graph is a dense graph, right, and this graph where there are very less edges, so this graph is the sparse graph, right, but this one is dense graph, right. So for such graphs which are very sparse, it's better to use adjacency list. Now this is the diagrammatic representation of adjacency list, right. Now this is I think this is sufficient for the introduction of graphs, and in the next lecture we will be doing a case study where there is a traffic light problem, and we will be solving that problem using graphs. Thank you.